Here are solutions to homework set number 5 for ECE 320. The first problem is set up a 555 timer and determine the on time, off time, and frequency for the following 555 timer circuit. Now with a 555 timer, the time is R times C times log of 2. So when I'm charging R1 and R2 in series, that'll be 30K. And let's see if we can get this over here. And there's C. So the on time is 2 milliseconds. The off time is when discharge gets grounded. It just discharges through R2. So that'll be 1.386 milliseconds. In Circuit Lab, I can simulate it, build a circuit, do a time domain simulation. Again, here I can't do a DC simulation because the voltages are changing. So for a time domain simulation, I can sit there and see the voltage at the output being set, clear, set, clear. This is the voltage on the capacitor, charging up to 2/3 of 5 volts, discharge down to 1/3. Charge up to 2/3, discharge. When I'm charging, I'm going through R1 plus R2, discharging just through R2. And I can check. From Circuit Lab, I've got the on time is 2 milliseconds, off time 1.4 milliseconds, pretty close to what I calculated. And hardware, we'll see if this works. In hardware, I can try that. And here's what the circuit looks like. So this is my power supply. There's my 555 timer. If I take a speaker, like this guy, with 200 ohm resistors connected in series, take one to ground, the other one to the output, and find it. The output is really quiet. Instead, if I use the transistor as a switch, that's what this one is. That transistor switch will come up in just a second. So the circuit with the speaker and 200 ohm resistor is really quiet. To amplify it, I need to add a transistor. So to do that, the 3904 transistor can only handle 200 milliamps. 5 ohms at 5 volts at 8 ohms is 625 milliamps. That's too much. So I need to increase the resistance or drop the current. This makes it 28 ohms. 5 volts at 28 ohms is less than 200 milliamps, so that works. What I want to do to find the base resistor is pick this so that the transistor saturates, and the conditions for saturation, if I could do it, I want, worst case, the gain is 100. 100 times IB to be greater than IC. That'll saturate it. So the current that I need, let's see, 5 volts over 28 ohms. I'm trying to push 179 milliamps. Divide by 100. This has to be at least, IB has to be greater than 1.79 milliamps. And less than 25 milliamps, because that's all the 555 timer can put out. So pick a resistor to set RB bigger than 1.79, less than 25. 1K works. When this is a 1K, I've got 5 volts here. There's the diode, 0.7. 4.3 volts across 1K gives you 4.3 milliamps, more than I need. That should work. So that's what I expect to get. When it's 0 volts in, it should be turned off. 5 volts in, I should saturate the transistor, 0.7 volts at the base, 0.2 at the collector. Throw this in Circuit Lab, and it's almost what I expected. The base is close to 0.7. Again, transistors or diodes are not ideal. It's not exactly 0.7 volts, but should be close. The collector should be close to 0.2 volts when I saturate it. Circuit Lab says 0.2417. Now let's build it. To limit the current, I get a loud sound. Take the second transistor, right here. This is an on-off switch. Okay, so notice when I add the transistor, I go from a quiet sound to a loud sound. I get more current. That's what transistors do for you. In fact, what I can do is add a second transistor. Scroll down a little bit. I've got a second transistor right here. When this is 5 volts, this one turns on the speaker. 0 volts turns it off. When I take the base and tie it to 5 volts, this one turns on, which turns on the speaker. So here's my manual, connect to 5 volts, on, disconnect, on, disconnect. Okay, so that's what transistors do as a switch. Suppose instead of having it turn on and off manually, I want to have it turn on and off with a temperature. That's when I want to convert temperature to a binary output. That's a comparator. If we use a thermistor, this is the one in your lab kit, 1000 ohms at 25 Celsius, and that's just a constant, kind of like beta per transistor. The way this works, at 25 Celsius, the temperature is 298. These cancel, gives you 0, e to the 0 is 1, 1000 ohms at 25 Celsius. As temperature goes up, the resistance drops. So this is temperature, there's R. To convert resistance to voltage, I use a voltage divider. So at 25, or actually 40 Celsius, the resistance is 533 ohms. The voltage from a voltage divider is 1.74 volts. This 1K is kind of arbitrary. It tends to work best if you keep these close to each other. So I'm going to switch at 1.74 volts, which is 40 Celsius. In terms of plus or minus, as the temperature goes up, the resistance goes to 0. So when it's really, really hot, V5 is 0. Really, really hot, this is 5 volts. So 0 volts in gives you 5 volts out. That's why I connect to the minus input, or it kind of gives you this. The circuit cares about voltage, not temperature. 0 volts is hot, 5 volts is cold. I want to turn on when it's hot at 0 volts. So connect to the minus, and that's what I should get. In Circuit Lab, I can check, build the circuit, and instead of the voltage divider, I'm going to use a sine wave. As the voltage goes up and down, when it passes through 1.69 volts, the output should go high and low. Bigger than 1.69, it goes 0 volts. Less than 1.69 gives me 5 volts. That turns on and off the transistor. If I do a time domain simulation, that's what I see. As the voltage goes up and down, when it goes above 1.69 volts, the output goes off, transistor's turned off. When it goes below 1.69 volts, the output goes high, the transistor's on. And if I look at the current through the speaker, here's what you see. When the transistor is off, there's no current flow. When it's turned on, I get this square wave. That's the 555 timer. In hardware, I can try that. With that, I can then take it to a comparator. The comparator is this guy. When the voltage, here's the thermistor. Voltage divider. When that goes above the B minus, which is set to 4 volts, the speaker turns on. So when it gets hot, let me pause for a second. Now I'm showing the voltage on the thermistor. As it warms up, it goes above 2 point. As it warms up, the voltage will drop. When it drops below 2 volts, the speaker should turn on. Here's the hairdryer. So there it turned on. I let it cool down. When it goes above 2 volts, it should turn off. Two volts-ish. Problem 8, as a Schmitt trigger, I want it to turn on at 30C, off at 35C. Pause. Okay, so that's a comparator. The on voltage is the same as the off voltage. Problem with comparators is, well, here's the circuit as a close-up. So here's my 555 timer. The output goes right here. That goes to a 1K to the base of the first transistor. That turns it on and off. The collector goes to the emitter of the second transistor. And here's the speaker going to the collector through 20 ohms the base goes to my comparator, and here's the plus minus input. When this goes to 5 volts, that turns on this transistor. When the 555 timer is also 5 volts, this turns on this one, and I have a path to ground for the speaker. If either one turns off, there's no path to ground, the speaker turns off. Problem with the comparator is the on voltage is the same as the off voltage, so if there's noise at the input, I'm going to go plus minus, plus minus, plus minus. It'll chatter, turning on and off. To get rid of the chatter, what I do is instead of having that, I create a little Z pattern. So the on voltage is different than the off voltage, or the one we're using actually goes this way. Since I want high temperature to be on, meaning low voltage turn on, I'll have a Z like this. So this is V5. As V5 goes up, meaning colder, the output turns off. As V5 goes down, meaning hotter, it turns on. It should turn on at 45 Celsius, turn off at 40. To calculate the Zener, the Schmitt trigger, the on voltage right here is your offset. When the input is large, the output should be low, connected to the minus input, and the slope is the resistor ratio. Output changes by 5 volts as the input changes by 0.2, 23 to 1, make this 23 to 1. If I build that in Circuit Lab, like so, I now have this comparator have positive feedback. That's now a Schmitt trigger. If I look at the voltages, make the input the Schmitt trigger. Here's my voltage divider. I use the sine wave instead. As it goes up and down, here's the off voltage, here's the on voltage. And notice that they're different. So here's off, there's on. That little dead zone right there is the hysteresis. That's what comes from the Schmitt trigger. If you look at the speaker output, when the op amp, the Schmitt trigger is 0 volts out, the transistor is off. When it's 5 volts out, it's on. And when it's on, the sound comes from the 555 timer. To illustrate that, I've added this resistor right here. That's my positive feedback for Schmitt trigger. It should turn on at 2 volts and turn off at a different voltage, a higher voltage. That's the hysteresis. So turning it on. Well, it should turn on at one voltage, turn off at a different one. So that's homework set number 5 for ECE 320.